Test. You hear me, everyone? Online, YouTube. Huh? I should shout? Oh, okay. Okay. And can I have?
This the pointer. You cannot move the slide.
I cannot what?
Move the slides. Quick.
I see.
There's no enough.
Okay. Oh yes, that would be really helpful. Yeah. Yeah, sure. Yeah, absolutely. Why not? Thanks. Okay. So can I start? So I mean, it's the Thursday before Thanksgiving, so everyone is struggling to. Oh, okay. Well, I mean, so before I start, just because everyone is here and it's Thursday, it's the Thursday before Thanksgiving. Black Friday is coming up. Turkey season is coming up. I will feel like everyone deserves, something for making it this far. So please, I have like cookies and like wafers here. Please just take one and pass to just make sure you return the bag, please. Yes, please. Everyone gets something. Yes, it's for everyone. But I have a Kool-Aid here for participations and interaction. Yeah, absolutely. We made it this far altogether. So yeah. Yeah. So my what I'm going to be talking about today is Google neural network models for edge devices. Basically, the concept, the idea behind today's talk will be we are going to be analyzing what the bottlenecks are in neural network models for edge devices, and also figuring out how we can mitigate these bottlenecks. Just as an introduction, my name is Ezekiel, third year PhD student in computer science. My focus is in bioinformatics and computational biology. I feel like there are like few things going on so well for my presentation. The first thing is because my focus is in bioinformatics and I'm presenting on neural network models. So, and I'm presenting alone by myself. So yes, just to give an executive summary of what we are going to be talking about today, we're going to be talking about edge TPUs. So edge TPUs are accelerators, machine learning accelerators that are designed to, to perform neural network inference at the edge. But the problem with edge accelerators designed in such a monolithic way is that usually in the real world, when you test this against real neural network models, you find that the design is inefficient for these models that they are handling. And so the core idea, the core scope is to design an heterogeneous framework that will allow you to run your neural network models on specialized accelerators that can handle specific workloads. And so the result will be, or the result of that framework, of that approach that I'm going to be describing later on, will be a 3 times increase in the speed up and a 3 times increase in energy. So How many of you use a Pixel phone here? Really? No one uses a Pixel phone? That is crazy. You guys need to come to the good side. So I use a Pixel 6a phone, and yeah, that's the picture of the phone. And the promise is that for everyone here understands this, is that our smartphones or smart devices, they're going to be running machine learning or inferences like all the time. That's the promise. That's the reality of the world we live in nowadays. Yes. Yes, promise machine learning will be everywhere. But so a couple of months ago, I got this message on my phone. My phone can just blow up because of batteries, and so because of damaged battery. And so Google has pushed a software update to my phone that will such that if I'm actively using my phone for like 4 hours, I have to be looking for a charger, you know, for some whatever reason. So promise is that we're going to have smartphones, smart devices, edge devices that can handle machine learning inference fast. But the problem is no one wants to talk about how we're going to facilitate this. What is the battery capacity? Yes, next slide. And so this begs the question, machine learning inference on edge devices, they drain our batteries so fast. Why? Why do you think they drain our batteries so fast? Huh? Exactly. Oh, yes, you get a Kool-Aid. Something Kool-Aid man. Yeah, if I can figure out how. Yes, memory bottleneck for sure. Oh, can I toss it? I could toss it. Yeah. Yeah, absolutely. Yeah. Okay. Good answer. So the amount of memory, the amount of throughput that we're demanding from our devices nowadays is a mismatch for the battery capacity. And so there is a bit of conflict in that area. Next slide. So I'm going to talk about edge devices, something I call the impossible triangle. Think about cloud computing. Cloud computing, you generate your data, you send it to the cloud or some data centers, in some data center somewhere, and you get your results. With edge computing or edge device, you have edge devices. You generate the data, and you want to process the data right very close to the source, you know, or on the source locally. So you have a trade-off between you're demanding high performance, you're demanding low power, and you have a small size. So that's the trade-off. For cloud computing, you can, if you want to increase the performance in your data center, you can just add more hardwares, right? And if you want to be more power efficient, you can use some thermal cooling or whatever. But you don't have that kind of flexibility in the cloud. And so there's trade-off in what you can do with edge computing and edge devices. As much as we want to use them, as much as we want to have access to them, we have limitations in what they can actually do. And so how do we measure edge device? How do we measure the performance of edge computing or edge devices? And I'm going to use one of our favorites. If you trade stocks like Tesla, the Tesla car, how do we measure the performance of the Tesla car? First, how quickly can the vision system? How many of you drive a Tesla? Oh, still up and coming, very soon. So yeah, how quickly can the vision system detect that there's an object and can trigger braking? Do you want to be what? You want it to be able to quickly detect an object and trigger braking, that is latency. Okay, so you have to have really small latency, and also if you're using full self-driving, how much energy should the system use, and how effective should it be with energy? So that's one of the core pillars of how we measure the performance of edge devices. And the last one is with all the there are like maybe like 8 different cameras recording constantly on the Tesla. How fast should they record and send data to the sensor so that you can be able to actually drive the car? That is throughput. The goal is you want to minimize latency, you want to minimize the energy, and at the same time, maximize throughput. Okay? What are the existing solutions that companies or that exist for solving these core pillars of measuring or of improving edge device performance? First, the CPU. Here I'm just showing the Intel Core i9. We see the power. I'm not going to go deep into like, I'm just trying to show you just the 4 pillars of existing solutions. You have the power, you have of a CPU, it consumes a lot of power, throughput has really good throughput, latency, it's not that bad. GPU, I'm showing the NVIDIA, I think, Orion, I'm not really sure, I forget the name, but you see it uses a little bit more or less power, but it has like a higher throughput, also relatively same amount of latency as the CPU. FPGA is another solution that exists. The AMD Spartan chip has lower power than CPU, uses low power than the CPU and the GPU, and also has low latency. And you have the ASIC solution, which ASIC stands for Application Specific Integrated Circuits. And here you can see it uses low power, has pretty good throughput, and it has like really nice latency. And so in general, ASICs have emerged as the leading solution for edge devices, but we actually need to actually quantify if they work. So this is just a table to show you kind of like the trade-offs between all these existing solutions. But today we are going to be talking about Google Edge TPUs. Okay, just to set some kind of context here, I'm showing you the Edge TPU that is used in data centers and the Google Edge TPU that you can find in your, it actually fits inside of a pen drive. So it's very, very small. Yes, next. And to give you like a more visual context, this is the Edge TPU chip in data centers, and you see this small this red dot is that's the size. That's going to be the size of the Google Edge TPU in comparison to, because the previous pictures can be deceiving. So you can see the size difference, and you can actually compare how different they are. This is I'm showing the data center Edge TPU, which is like the first version and the specifications. And for the Google Edge TPU that actually exists in a USB drive, basically. And when I was reading about this paper, I found something very interesting. And what I found was like this data center Edge TPUs. If you want to, you cannot even buy them. If you want to rent a 512 TPU, Edge TPU from Google, it costs $1.2 million per year. So those things are very, very expensive. So the idea here is can we actually maintain the efficiency of Google Edge TPUs while also working with a limited power budget? Okay, so I'm going to be just giving you like a quick, just a quick understanding of how the Google Edge TPU works and what it looks like. So you have the DRAM. The DRAM stores the models connected to the processing element array with an off-chip bandwidth, and you have a processing element array of 64 by 64, so it's pretty large, and 4 megabytes on chip buffer, and you have a static or a fixed data flow. And so, but just 1 second. Yeah. So the models are stored in the DRAM, and they get shipped into the processing array layer by layer as they are needed. What do you think what could go wrong with this? This is the solution that Google has come up with for edge devices. That okay, this is going to be if you need compute, this is a large processing element array. We have on-chip buffers to store input activations and stuff like that. What do you think could be wrong? What do you think? What could go wrong? If something were to go wrong, what could go wrong? Right, exactly. Right. So the PE array is just waiting, sitting, while it's just fetching from the memory, right? Okay. Any other contributions? No? Okay. Cool. Yes. So when we actually test this architecture against real world neural network models, what was found was that the average processing elements utilization was about 24%. And basically, the architecture spends 50% of the energy just on DRAM accesses.
You tell normal mobile without PQH.
Right.
It's also waiting for data.
Yeah, I mean, so exactly. I mean, I don't.
You have a GPU having a memory box.
Say that again. I don't know.
Second thing is they said that these are waiting for data.
Right.
Any other edge device is definitely waiting for that much.
Yeah, but the idea here is to make it a little bit more effective. Yes, we agree. Memory will always be something to consider, but how can we make it more efficient, effective? Yes. Okay. And so they try to we need to look into why this design is very poor. Why is it performing very poorly? The first problem is think about LSTMs and transducers. What do we use them for? I mean, what kind of models? What kind of neural network models? Oh, no, that's not the question. The question is, what kind of applications do LSTMs and transducers? What are they actually do? What kind of applications do they do? Yes, exactly. And so, oh, okay. This is my very good. Thank you for helping. So what the problem with this when you test them against, when you test the energy that LSTMs and transducers, these are real neural network models that are used. When you test and you see how they use the energy, you see that they spend much time just accessing the DRAM and transferring the models from the DRAM to the actual processing. So they spend a lot of time just making trips, while the processing element array is just like, anytime now, I'm ready. Okay, so that is the first problem. The first problem is that LSTMs are and transducer are memory bound. So they need to be optimized for that particular application. And the second problem is that if you think about applications, CNN layers, you find that across the different CNN layers, you find different MAC operations, or how, like, the compute power, the compute value across different layers different. For example, look at this layer 21 here in this CNN3 layer, and look at this. They have very different MAC profiles, basically. And not only that, which I think is very interesting, and you see different MAC operations or MAC profiles even within the same CNN layer. So for example, if you look at this CNN 11, it has a MAC operation of maybe 13. And if you go down, you see very, very low MAC profiles. So first problem, the second problem is that this the CNN layers varies across different layers, and also it varies within the layer. So those are the roots, basically the root cause. So we've established that. And we can see that, so for example, if we take this CNN 13 and we plot the parameter reuse against the parameter footprint, we can see different layers have different properties, basically. So that is a problem. So we assume, or we say that since every layer is unique, we need to design a custom accelerator for each layer. But what is the problem? It's impractical. It's an impractical design. We cannot design accelerator for each of the different layers. And so what do we do? And this is the you have a question, sir? Oh, this is the key idea of the paper. And if you don't remember anything, once you remember this, I'm fine. I did everything I need to do. Okay, so the key idea here is that even though these layers, they might look different when you plot the parameter use and the parameter footprints, they actually cluster into different families. Okay, so they cluster into different families based on the characteristics of that particular layer. So yes, so the vast majority of the layers of this neural network models, they cluster based on the compute intensity, and based on the parameter footprint, they cluster into families. And I'm going to just, because this is the important part to understand in the whole talk, I'm going to show you. So the first family here, this is the plot of the parameter reuse and the parameter footprints. Maybe before I go into this, can you go? Why I needed to understand this, so you also need to understand. Why are we plotting the parameter reuse against the parameter footprint, and plotting the parameter reuse against the number of MAC operations, and not, say, for example, plotting number of MAC operations against the parameter footprint? Does anyone know why? Any intuitions as to why? No? Okay, right. I will make that clear in a little bit. So for the first family, you have families that have a very small parameter footprint, and they have a very high parameter reuse. Okay, so the intuition behind this is that they are convolution layers. And with the second plot, with the parameter reuse against, plotting the parameter reuse against the number of MAC operations, you see that they have very high MAC operations. And that intuitively tells us that this family, they are bound by compute. That is, they do a lot of math operations. Why? Because they have high they have high mark operations, and they have high parameter reuse. And so to effectively to effectively design something to work for this family, you need to design something that actually takes advantage of the innate compute characteristics that this family has. Yes, so the first family, the second family, you see here, they have medium parameter footprints, not as low as the first family. They have moderate parameter reuse, and they have really high mark operations. Okay, and so that still establishes that they are compute bands. That means you need to provide. They need more math operations. They need to access the processing element as frequently as possible. And then for the third family, they have large parameters, and they have very, very low parameter reuse, and they have little to no mark operations. That is, they don't do any math, and so they are bound by memory. Okay, so they need to be very close to some source of data, because they don't really use they don't do any math operations. And the third family has large parameters. Oh, sorry, I said third, the fourth. The fourth family has large parameters and low parameter reuse, and it has medium mark operations. And for the last family, it has small parameters, low reuse, and medium mark operations. So to answer my question for why we are comparing the parameter reuse against the parameter footprint and parameter reuse against mark operation, is because the parameter reuse is what actually tells us whether a family is bound by compute or it is bound by memory. So for example, if you have a high parameter reuse, then you're definitely accessing the processing element, or you're bound by compute. And if you have low parameter reuse, you need to, perhaps you are using more memory. Is that clear? Ish? Okay. So the idea is, instead of creating one monolithic accelerator to handle these different types of workloads with LSTMs, transducers, CNN layers, why design few accelerators that caters to specific families, that caters to what each family is good at or wants to do. And so this is the core idea behind Mensa. Mensa is a framework that routes layer families or layers in a neural network to an accelerator that is designed specifically for that family. And to give a more visual context, different layers is sent to a scheduler. Scheduler matches the layer to the best accelerator for that particular workload. And so it is, sorry, I need to drink water. This is based on two design principles. The first principle is that, again, like I mentioned, you need to match the engine to the workload. So for example, if you have a large processing element array, then these are compute bound layers. So you need to provision more processing elements, or you need to make sure that the processing element actually matches the layers, or basically so that the processing element is not just sitting and waiting. And for the memory bound layers, you need to make sure that it is very close to the source of data, so it's not it's not being limited by memory. And so, and the second principle for designing Mensa is to make sure that you're minimizing inter-accelerator communicator. Sometimes, instead of matching the layer to the best accelerator, it is better to run the layer on a suboptimal accelerator in order to reduce inter-accelerator communication. That is, so no, just go back. Yeah, so the first part, make sure that you're matching the engine workload, make sure that the accelerator, the hardware matches the workload that you're using. And also the second design principle is that make sure that you need to reduce inter-accelerator communication as much as you can. So sometimes you might run it on a suboptimal accelerator if it's going to cost more to transfer it to the ideal accelerator, because you have to pay something. Okay. Yeah, so this just gives a more clear intuition for how the Mensa framework works. Okay, so now I'm going to introduce can you go back one slide? Yeah, so just to make it clear again, so you have the neural network model is passed to a runtime scheduler. These are the specialized loads, and the families are passed to it, and those accelerators run the workload. And so the first kind of accelerator that was designed or that was proposed by Mensa is called Pascal. So these are this is an hardware accelerator engine that is optimized for compute. So you have the provision a large processing element array. And the provision a small parameter buffer and activation buffer, and this is typically used for layers that have small parameter footprints. They need high compute, and they have high parameter reuse, and they also have large activation footprints. And you can see that instead of putting the die in the DRAM, they put it in the CPU because they want to minimize DRAM access as much as possible. And so to explain the data flow for Pascal itself, okay, so this data flow is one of the key design principles for the engine, because this is basically allows us to understand how data flows in Pascal and what makes it more efficient. So you have the weights. The weights is distributed across all the processing elements simultaneously. And for in a cycle, so the weight is distributed across and held in the processing elements. And then in the next cycle, it reuses the same activation outputs, or the same output activation in the next cycle. So what this means, or the intuition, is that all the processing elements, they have the same weight in the same cycle. And also, what also means that it's the processing elements is accumulating the partial sum or the partial outputs across the different cycles. So instead of doing each sum at every single cycle, it just accumulates them. Next, the next engine is the Pavlov, which is optimized for LSTMs. In this case, again, if you're familiar with LSTMs, they have like huge gates, very huge parameters. And so they designed this engine for low compute. So they need to have high parameter. They need to have huge parameters. So they're designed to have a very high parameters and low parameter reuse. And so also they're designed for high activation use. So basically the die is put in the DRAM so as to make it very close to the weight that is going to use. And to explain sort of like what I understand from the data flow is, so the input activation is broadcast at the same time to all the processing elements, and the weight, the weight is held in the is held in temporarily inside of the processing elements, and in the next cycle the same weight is reused inside of that cycle. So you are temporarily reusing the same weight across the different cycles. So basically you're fetching the input activation once and reusing them. Then the next one is, or the last one is is called Jacquard, which is optimized for memory bound non-LSTM families. In this case, this family would have small activation footprints. They would have moderate compute intensity. And the idea here is that the same, just like before, the same input activation broadcasts to all the different processing elements. The weight is held inside of the processing elements. But in this case, the same output activation is accumulated across the cycle. Okay. Just to give an example of how this would work, I put this example. So you have different layers. So for example, this is a CNN neural network model, and you have the different layers, different types. You can see the different parameters, different parameter for reuse, different mark operations. And so, yes. Yes, so the idea here, like I mentioned, is to, for each layer, find the best accelerator based on the compute intensity, based on the memory footprint, and based on the family membership. So the first layer, you go layer by layer. The first layer, you assign the best accelerator. Second layer, you assign the best accelerator, and so on and so forth. And so that will give us this, basically this template. So you have layer one will run on Pascal, an accelerator optimized for compute. Why? Because you can see this has more very high parameter use and very high mark operation, and so on and so forth. But what is wrong with this, with having it like this? Like, what happens if we have this kind of communication between the different accelerators?
Same as in there.
Yes, exactly. So, oh, sorry, forgot. Kool-Aid. Yeah, someone said something else.
Same accelerators are also being again.
Exactly. So you can see that the oh yes, sorry. Oh, close. But yes, so you see that the accelerators are constantly switching. So in this case, for 7 layers, you have 6 switches. So it goes from Pascal to Jacquard, then to Pascal to Jacquard. So the cost of communication between these different accelerators is a very huge overhead. And so let's see how. So what I described before was the first phase, which was to match each layer to the engine. The second phase is to make sure that if you have a higher cost of transferring from one layer to another, make sure that you keep it on a suboptimal accelerator. For example, so the first layer was supposed to go on, this was this was an error. It should be Pascal. The first layer should run on Pascal, right? The second layer should run on Jacquard. But if, and it has for the first layer has 400 kilobytes of activations. So it means that you have to read it to the DRAM and then write it back to the DRAM before you can put it into the new accelerator. So now you have what, like 800, you have to spend power, for example, like let's say 4,000 millijoules of energy to do that, to transfer the activations. And so, but if you run it on the ideal accelerator, you get more efficiency from your processing elements. But if you keep it on the suboptimal accelerator, you might get like maybe like 40% utilization on the suboptimal accelerator, but it's still the same compute, it's still the same, almost the same overhead. And so if it will cost 7.2 millijoules of energy to keep it on the suboptimal accelerator, and to transfer it to the optimal accelerator will cost 4,000 millijoules, you should keep it on the suboptimal accelerator. And this way, you don't spend the cost of transferring from one accelerator to another. Okay, so, and this is the first heuristic. So that's one of the key concepts of the paper. It's not like something very, it's not like some profound, sophisticated idea. It's a heuristic, it's a rule of thumb. Basically, yeah. So if it will cost more to transfer, keep it on the suboptimal accelerator. Next, so when does it switch? Same scenario here. So you have layer 5 runs on Pascal. Layer 6, the perfect accelerator for layer 6 is Jacquard. And so if you do the cost analysis, this is the characteristics of layer 6. If you do the cost analysis, you see here, to run it on Pascal will cost 1.6 millijoules. But because of the huge parameters that this layer has, it will have to fetch the parameters, and it will use 6,000 millijoules of energy to fetch these parameters. And it will cost some processing elements overhead. But if you were to transfer it to the ideal accelerator, the transfer cost is just 4,000 millijoules. And so you have, you see the difference in energy. And so because it will be, you will spend a lot more energy here fetching the parameters, you transfer it to the optimal accelerator. Is it clear? So the second heuristic, if the parameter footprint is greater than the parameter used, and just switch it to the next accelerator. Yes. So and so this is what it's going to look like after we finish. All the first 5 layers will run in Pascal, in the accelerator Pascal, and like I showed just in the previous slide, layer 5, it will transfer it will transfer to Jacquard, and finally transfer to Pavlov. And so now, and so instead of having 6 different switches, you only switch twice, saving energy and compute. So this two-phase approach is what Mensa is proposing, or what the framework behind Mensa itself. So Mensa G is the implementation of the Mensa framework to Google Edge model. So they took 24 Google Edge neural network models, 13 CNNs, 2 LSTMs, 6 RNNs, and 3 RCNNs, and they clustered them into 5 layer families. And they used 3 accelerators, 3 engines. And yeah, so the result is what we are going to be seeing next. What they discovered was that Mensa, the implementation, yeah, you can, yeah, so, oh, yeah. What they discovered was when they when they checked the throughput, they discovered that Mensa on average improves the throughput when you compare it with just the baseline, and when you had a higher bandwidth to the baseline. Yeah. So Mensa was more effective with the throughput. And also when you check the energy analysis for Mensa on average, it spent it was more energy efficient on average, better than the baseline that spends like 70% of energy with on DRAM accesses and so on. So you can see how Mensa has here. You can see it just spends energy, a little bit of energy on DRAM access. So lower energy for Mensa G with on-chip and off-chip parameter traffics. For the strength of the paper, this was the first per layer analysis of Google Edge models that was presented, and they were able to show that layers clusters, even though they show the display heterogeneity, they actually cluster into families, and they were able to design the hardware. I didn't really talk a lot about the hardware, but they were able to design the hardware to fit into the current existing architecture of the Google Edge TPU, so they didn't have to design everything from the scratch. And yeah, so they discovered that for those 5-layer families, you don't need 5 different accelerators. You just need 3 that can handle at a high level these workloads. The weakness is that because the scheduler, or what actually decides where these accelerators run, is a heuristic, it might miss edge cases. And also the models that they trained it on is on 2019 model suite. So basically, in a world now that we have transformers, we don't know how that is going to how that will look like. And then they did not account for what is the cost for this runtime scheduler that schedules the workload on these different accelerators. And so for different directions, something that we can talk about is how we can adopt this framework to the modern workloads that we're using now. For example, the popular transformer architecture. Do we need do these actually cluster into existing families, or do we need a new accelerator for attention specific operations? That's something that we can look at. And also, do we design a more intelligent scheduler that can learn and adapt to the different layer types, but it's going to be online, and so on. So those are the different directions. So those are the ways that we can take this idea. And for the critics, it's more about like giving a comparison. So for example, Mensa has decided to like use just 3 specialized accelerator. Can we actually just reconfigure one accelerator to match the workload? So in this case, you're trading off efficiency versus adaptability. Should we be designing hardware for neural network, or should we be designing neural networks for hardware? So yeah. And the key takeaway, heterogeneity is structured sometimes. And if you have embrace and heterogeneity will be the key takeaway. And yes, yeah, if you would like to read the paper, this is a link to the paper. Questions? Oh, do you have any questions, basically, for me? Oh, yeah, yes, Kool-Aid. Yeah, anyone that says anything gets a Kool-Aid. Something Kool-Aid, man. And yes, please, for those who join later, please, there's, yeah, if you can help pass. Yes, please. No questions? Wow, that's not good. I didn't do good.
Overhead is that you have sample patient, because you have to understand is it compute bound or memory bound.
Right.
or
Yes.
it's setting in middle.
Yes. Yes.
The hardware configuration. You can actually configure hardware based off the dealer.
Yes. 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 That's a point.
Are you hinting at Google had a challenge when they did Mensa or
Uh,
they have done
I neither affirm nor deny. I plead the fifth. Yes. Yes, there's cookies and wafers. It's Thanksgiving. Yeah, so I just have two little questions for the class. What costs more in energy for Google Edge TPUs, for LSTMs and transducers? What was the main bottleneck for? What is the main bottleneck for in energy for Google Edge TPUs, LSTMs and transducers?
between each layer.
Memory, right? No? Yes, yes, memory. Yes, you get, yeah, you nodded, so. Yes, and then the second question that I had was, why does the scheduler sometimes, why does it keep some neighboring layers on the same engine? Why? To save energy, exactly. Oh, you have one already. You want to give one to your friend? It deserves another one. Okay. This time I'm going to throw well. Oh, shoot. I did throw well, though. Yes, that's, yes. Any other questions? That's, oh, still have more time for questions. Oh. Mm-hmm. Yeah, that's, yeah, exactly. So we prefer to keep them on the same engine if it's going to cost more to transfer them to another engine, because you have to account for the cost of transferring to the DRAM and then reading it again from the DRAM to transfer to the different layer. Does that make sense? To the different engine, basically. Sorry? So we can profile them, like, okay, this is going to be in this bucket, basically. Yeah. So we can say, okay, this is what we can expect from this family of models or of layers. Like, oh, this layers in this family are they have very high mark operation. And so we must consider, instead of thinking about like, oh, let's put them where they need memory, we don't think about memory, we just think about like, okay, they probably need some more compute. Does that make sense? There's more time. Heuristics, rule of thumb. So basically, like, how do I say it? Heuristics is just a rule of thumb. It's like, okay, if this is true, then do it. There's no. Right, exactly. That's what I'm trying to say. Like, when I think about heuristic, I think about like, right, right. When I think about heuristics, I think about like, my grandma telling me to, eat my vegetables because it's gonna make me grow tall, so. Oh, thank you. Yeah, yeah, very good heuristic my grandma gave to me. No, it is not an optimal solution. Because there are edge cases that is gonna miss. So for example, my grandma tells me, sometimes efficient, but not optimal. Okay, yes, maybe that's the right way to say it. Sometimes. Case where if we reduce the data transfer, it might not be optimal.
Or first, let's think about optimal in what sense? Which method?
Optimal in two things. Optimal in compute efficiency and in memory efficiency. So you want to reduce how much memory access that it does, and you want to increase how much processing elements it does, it accesses or it uses, or make it as much as possible. So to answer your question, an edge case for when can't think of any right now for sure. Uh-huh.
Why?
Oh, yeah. You need to know whether the application where you are deploying them is actually like a memory bound application or a compute bound application. What?
What do we call it? Category.
Profiling? I don't know. Sorry.
You mentioned what you mentioned.
Oh, yeah.
How did you explain this? Have anyone tried to run for the free software? The only requirement that can run into Windows, Linux. I would suggest like the how it works with provide that profiling, provide down and build subtypes. Based on that, decide. Right. Do you have any questions? Right. I think that you did a great job.
Thank you.
So let's take.
That was hard to think. So like very hard. It's actually very hard to actually.
Let's take 4 minutes break. I think he did a great job. The first version sent me was really bad. So I'm really surprised that he did that big leap. So yeah, I like it.
Oh, and please, yeah, anyone can just have. Yeah.
No, I cannot. No, you didn't ask any question, no?
Oh, yeah, please. We should take on it. Thank you. I'm selling $10. $10. Like a lot. Guys, send your slides. Not over today. Then my advisor. Yeah, I'm in. Yeah. Yeah. Second meeting. I don't. Also, I got the. Is it? Yeah, probably this is out of battery. You send it?
Hello, hello. Is it working? We can change slide using this. No.
No.
Should we start now? Okay.
Yeah, go. Yeah, give me the-
No.
But,
I'm not sure. I think no one is using this.
yeah, okay, no. Second fourth
Change
line.
না এটা চেঞ্জ হয় না আমি জিজ্ঞেস করছিলাম জিজ্ঞেস হয়
Take it to the pointer.
ইয়েস খালি পয়েন্টটা এটা চেঞ্জ হয় হলো ওকে ঠিক আছে Okay, good afternoon, everyone. So today we are going to present deep compression deep neural network with pruning, chain quantization, and Huffman coding. So I'm Apu Kumar Chakroborti, and these are my co-presenter.
Abdullah, Rahat. And my name is Aryan.
Okay, next. So anyone can say this, like, what is important in this slide? Any guess? Huh? Citation, right? Almost more than 12,000 citations. So is there anyone already cited this paper? No? Okay. Okay. Okay, these are the contents we are going to discuss today. Okay, next. Okay. So we already know that this is our brain, right? And this is the neural network, and this is the neuron in our brain, and this is the like unit of our brain. So any guess how many neurons like may have in our like in a human brain? Any guess? We have chocolates. So any guess? Yeah. Okay, go next. It is actually like based on the Google search 86 billion. Okay. Okay, go next. So we also know that. So this is our like a single neuron. Like so based on this idea, the like unit of the like neural network is formed. So this is called perceptron. So what does like contain a perceptron? Like input, weight, bias, summation, activation, and outputs. So the activation function, if there is anything like special in this input and in this weight, then it will activate this by like 1, and otherwise it will inactivate this by using 0. Okay, go next. Okay, this is a like neural network. We know that there are some multiple layers: input layer, hidden layers, and output layers. So what is special? So go next. Next. Okay, so we have weight matrix. Sorry, I think due to the transformation the weight matrix is like dropped. So this is a weight matrix we need to use in this, like when we need to chain or back propagation or something like that. But in the later, so this is a simple network, but this is a deep neural network. So any guess? So any guess like what will be the like weight matrix, like what change will like happen to the weight matrix? Bigger? Yes, you got it. Yeah, so that means go next. There will be large weight matrix, right? So go next. So in this week, actually the concepts are so similar. So I think last week this is also present by I forget his name. So maybe Mansoor. So we know that in 2019 the when the GPT-2 model was released, so only 1 billion parameters. Now like GPT-Neo X in 2022 20 billion parameters, 100 billion parameters. Then Palm is 500 like 40 billion parameters. So according to the like previous. So according to this parameter size, any guess about like what might be the size of these models? Like if we store this after training, if we want to reload and reuse them, right? So we need to store them. Like what might be the size of this? Like we can use any like floating point like precision, for example, 32-bit or 16-bit. Trillion bytes, yeah. Next, yes. So if we don't use FP32, if just we use FP16, still we need 1.8 trillion bytes. Okay, and initially it was only 3 GB, right? So this type of model actually we can't use efficiently if we don't have like good hardware, right? So go next. So the question for everyone: what is flops? Yeah, good. Like what is teraflops? Huh? Okay, go next. Okay, it was a silly question. Okay, teraflop is 10 to the 12 operations per second. Okay, so why actually flops matter? So flops, like more flops means like the hardware is fast, like can compute more operations in a per second or per unit time. Okay, it is also critical for training as well as the inference. So if the hardware is not good, if we compute the model in any hardware which is fast, but reload them by using another hardware which is slow, then the good performing model also will not perform well. Okay, go next. So this is the actually motivation of our paper. So there are different types of application, like application as well as hardware and devices. For example, cloud AI, mobile devices, and tiny AI. We can see that the memories are different for the tiny AI, mobile AI, and cloud AI, as well as also the computation powers are also different, right? So if the larger model, like even if the performance is good, we can't use in our day-to-day life because we always don't like have laptop or cloud AI access everything, right? Everywhere. Even if we have access, but we can't access them. But if we have that model in our mobile, we can use them anywhere, right? So that is why we need to like, but even if we want to compress the model to use in the limited memory, like devices which have limited memory and computational resources, but the performance should be also good without like the keeping the same accuracy or same performance. We may don't want to like, we may not want to use that. So this is our like intention in this paper. So we want to do. So these are the techniques. How can we compress the model, like pruning, quantization, weight sharing, hashing, knowledge distillation. So this topic is already discussed in the previous like week. So we are not going to discuss it, but except all the things we are going to discuss, for example, pruning, combination of pruning and quantization, and Huffman coding. So pruning. So what is actually pruning? So for example, we keep a threshold. So we want to keep only the weights, whichever the weights is greater than 0.1. For example, here we can see that the two weights like value is 0.1 and 0.1. So then we can see that this connection has been removed, right? Removed. So this is called pruning. So go next. So yeah. So this was the, for example, a toy example. So this was the weight matrix for the like large network. But if we like prune the network, we can have this type of like lower matrix or like smaller matrix. So this is why we need pruning. So lower matrix means we may need to like to give any inference result, we need to do less matrix multiplication operation, right? So yeah, see, for example, a large matrix size may be like 512 GB, but we can reduce it to 20 GB, right? We can, so quantization. So for example, we have this like 3 vectors, vector 1, vector 2, and vector 3. Why this happening this? Can you change the view? নোটা মাত্র দরকার না এই যে ভিউটা how to change the view not visible. Okay, sorry. So for example, we have 3 go back. Yeah, for example, we have 3 like vector 1, vector and vector 2. So if we calculate the like binary representation of each number, so this is the like 32 bits binary for each each floating point number. So for each vector we need 32 bits into 4, 128 bits size of each row. So definitely we don't want to use this like storage to store these vectors. Go next. So what can we do? Go next. So we can divide in quantization. We can subspacing. So we can use subspacing. For example, we can divide each vector into, for example, based on the like value we want, like m, based on the m, m equal to, if we say 4, then it is 4 part. Each vector has 4 parts. Then go next. So we can group them together, and then we can use quantization. Then by using quantization, we may have some cluster centroids, and each cluster centroids may have like some index, for example 0, 1, 2, and then each original vector we can transform as a code book. So this is called quantized vector 0, 0. Like each number is representing by 0. That means and this number is representing by 255. So that means we are using like 8 bits integer to represent all of this number. But is this like enough? Can we compress more? Yeah, definitely yes. So Huffman coding. So how many of you know already this Huffman coding? I think yeah, we should like we have this idea from the bachelors. So even if like after quantization, if we like we can say that the indices or the integer representation of the floating point number are repetitive. So still we need 56 bits. So we can like compress this too. And Huffman coding is a lossless compression. So we can we don't lose any performance even if we compress this data. So the step is note. We have nodes, for example, unique values 1, 2, 3, 4. We have counts, like 1 is 3 times, 1 is 4 times, 1 is 3 times, 2 is 2, 3 is 1, and 4 is 1 time. Okay. So go back. So yeah, so we in Huffman coding we need to form tree. Like we need to insert at first node 3 and 4, and the parent node would be will be the count of the each node, like 1 and 1 will be 2, and go next. So now we are inserting 2. Go next. So similarly we are like added the parent node after 2 and 2 is 4. Then go next. So now we are going to insert 3, and this is the complete tree. Yeah, this is the complete tree. Like 4 and 3 is going to be like 7. Go next. So this is the completely from tree. So we need to level this path. Go next. So we can see that the green like right 1 and left is 0. Go next. Yeah. So we can label is node. For example, 1 we can represent 1 or 001 we can say, or for 2 00 and 3 010 and 4 011. So we can only use 12 bits for each like vector. So this is how we can use Huffman coding to compress like 56 bits to 12 bits only. Okay, thank you. The next part will be discussed by our co-presenter.
I'll be discussing the executive summary. So let's discuss the problem here. So the problem here is the growing nature of our state-of-the-art neural networks and the limited resources of computer and mobile hardware that we possess today. So these large models, large language models, and require massive amounts of memory, and forcing the hardware to fetch data from DRAM, and which is very computationally and memory intensive. So to tackle this problem, they came up with the solution of deep compression. So it is a novel three-stage pipeline, and it consists of three major steps. Number one, pruning. Number two, quantization. And number three, Huffman coding. So after they conducted their experiments, they were able to achieve massive compression with no loss of accuracy. And so far here, in the end, they were able to achieve the compressed model was able to fit into the on-chip SRAM instead of the power-hungry DRAM. Because on mobile processors, we can only fit the model on the on-chip SRAM. So because they were able to fit the model into SRAM, so they were also able to improve the performance of the model. So as we can see, there is a 3 to 4 times speed up improvement and 3 to 7 times energy efficient. So now I'd like to explain fully connected layers and the convolution neural network. So in fully connected neural network, you can see that every node of the input here is connected to every other node of another layer. And then, and each of this connection here, each of these lines, they have their own weight, but that is not the case in the convolution neural network. As you can see that only the first two nodes of the previous layer is connected to the next node. And then, so in convolution neural network, you can think of this as a feature extractor or a filter. So in here, the same node is being used in all, the same filter is being used here in every node. Just the inputs are different. Input 1, input 2, input 2, input 3. So just the inputs are different, but this filter is the same for all the node here. And so now, so for this one, so this is the first existing paper that they had to look through. So the main idea of this paper is they introduced the idea of moving away from the expensive 32-bit floating point math, and they introduced the fixed point integer representation of 8-bit. So after they ran the experiments, they were able to solve the computation bottleneck, but it's still at the problem of storage bottleneck. But this paper did help them to do further research on weight sharing to reduce the storage size. And this is just a basic methodology of the paper. So first what happens is they obtain the quantized weights from the high precision weights, and then they were like put onto the feed forward layer, and the error was computed, and the after the back propagation, they were able to update the high precision weights. So this is the second paper. This is the second paper, and this paper introduced the idea of weight sharing as a technique to reduce storage by using a hash function. Okay, and so this is the third one, and this is the most important paper. for this paper. So the author of the deep compression paper, before they wrote this paper, he was busy building the foundation for the pruning part of our paper. So the main idea of this paper is that it established the foundation of the iterative magnitude and pruning. So the main three-step pipeline here is train, prune, and retrain. And after this, they were able to achieve a 9 times pruning on the AlexNet network. But pruning alone was not sufficient. There were still like remaining 32 bit weights that they needed to compress. But this did give them the idea of combining the idea of this paper with the other papers and then creating the current pipeline for our deep compression model. And so this is the figure from that paper. So here's what is happening here is that first the connections are getting trained, and then we prune that connections, and then we again train the weights, and then again prune the connection, and we keep on doing that. And as you can see, before pruning, the network will look something like this. But after pruning, as you can see, a lot of connections have been reduced here. And
okay, I'm Abdullah. So I'm talking about the actually these papers. That is deep compressions. Here, this paper is basically 3-stage pipeline, and uh, do the this process is first they do the pruning. So pruning is the it means that less number of weights. That means that how can we reduce the number of the weights in the networks. So this is pruning. That means in neural networks, when we train the networks, then there's some weights maybe close to zero. So we think of that there's a less contribution in the next decision. So we can remove the this connection or these weights, or sometimes we make these weights actually zero. So this is the pruning concept. And in this paper, they actually first train the networks and the prune the networks, and they retrain the weights. So because if you prune, actually is reduce the accuracy. After retraining, you will get the accuracy back. Then you do the pruning again, and you do the iteratively until you can prune without losing the accuracy. So in this case, they get the around 9 to 13 times reduction of the full models without losing accuracy. Next step, they use the quantization. This is another steps for the compressions. This main motto of this technique is that less bit per weights. So that means you are reducing the number of the weights. So that means that you do not need the bigger precision. So as you have in the model has the fixed number of the weights, you can feed them with the fewer bits. So this is the main concept. And here they do the works in this way that another level. There's the first prune weights, they actually do some clustering using the Kamin's-like algorithm, and then they get some centroid. So they actually do some centroid, and they make the centroid as a code book, and then use the code book to replace the weights correspond to the centroid. And then retrain the code book, because if you do this process, you may lose some accuracy, and you retrain the these weights in a way that so that you can get back the accuracy. So after doing this, they actually have a around 27 to 31 times reduction of the models, and more details will be discussed later. And the Huffman coding, this is the another interesting. We will already talk about the Huffman coding. So main thing is that more frequent weights must be represented by least number of bits. So suppose in a as you are sharing the weights using the quantization, so there is a lot of same same numbers in the networks. So if we can group the highest frequent weights and then represent by the only one bit, that means we are reducing the huge huge space, because this is the main. Much of this we will see later more. Okay, there is a pruning. Pruning can be local or global. So local pruning means that you are applying the pruning layer by layer. So if you remove the same percentage of the um, weights from the east layer, this is actually local pruning. And global pruning means that you will select a certain percentage of the weights of less importance from the whole networks. So my question is that why global pruning is usually preferred? Anyone can answer it? Why? What is the problem with the if you remove the fixed number of attributes, weights from the east layer? Okay, this actually there is some okay, but answer is correct, but my answer should be like this, that if you remove the more same weights, same connection from the east layer, that means some layer may be more important, more sensitive to accuracy. So just like a convolution layer and in CNN and the fully connected layer, convolution layer hold the special information. There is some more deep features controlled by the convolution layer. If you apply the same percentage reduction in this every layer, that means you are removing the some important features from the convolution layer. So that's maybe reduce the accuracy. But global pruning in these cases, if you apply the whole networks, so you are removing the least importance from the based on the whole networks. So that is the benefit. Okay, thank you. So another idea is that one shot and iterative. So one shot means that you just train, prune, and fine tune. So that's enough. So you are doing the one-time pruning. So this is aggressive a little bit. So is maybe sometimes affect the accuracy much more than iterative. So iterative technique is that you train, you prune a little bit, then you fine tune again, then you come back, prune again. So this is iterative. You are doing small steps every time. So that's maybe more stable, maybe more better. But what is the problem? Iterative. Do you think? Which one? Maybe overfit. Difficult to say what. Maybe Uberfit is I cannot show it, but main thing is that it takes more times. So you are iteratively doing again and again. So you are doing the same things again. So it takes more times. But I think your question maybe also correct. Another thing is the sensitivity analysis. So one thing they do is that all layers may not be same importance. So we can run some sensitivity analysis here, that we prune the some weights from each layer and we observe the accuracy. So in this way, we can understand which layer is more important, which layer is less important, which layer we can prune more. So in these cases, a fully connected layer is less sensitive to accuracy, and then we can prune up to around 90% without losing accuracy. So this is all, and next part will be continued by Apu again.
Okay, everyone, again I am back. So what is pass matrix? What is the disadvantage of sparse matrix? Zeros more, but the non-zero values are important, right? So they actually suggest an idea. So how can we efficiently store multidimensional data by using one-dimensional data by keeping track of the non-zero values only, as well as also keep the index difference of the uh, non-zero values. So even if there is no non-zero values, so if there is a long gap, then the integers like need more bits for the difference. So that is why they use filler zero, right? So there are two types of like this matrix, like compressed first row and compressed first column. So in this way we can store the data efficiently, and when calculating the parse, like doing some computation by using parse matrix, we can use that that one-dimensional array. So next. So now code book fine tuning. So in this work, they did some quantization, but sometimes the quantization lose accuracy due to the quantization. But they tried to cope up with the accuracy by using some fine tuning method. So while back propagation, so next. So they calculated the gradients of the same weight matrix, and they group them up to the gradient matrix. Okay. So then next. What they did, they tuned the cluster centers by using the gradient. So previously the cluster centers were this, based on these weights, and they just by using the gradients and in calculating back propagation, they updated the cluster centers and updated the code book. Next. So quantization space. So quantization space means, so while doing quantization, like it is a lossy compression, right? So we may lose accuracy. So for that we need to use think about the quantization algorithm should be good. So they think about two types of metrics, like CDF and PDF. So CDF is cumulative density function and probability density function. So the blue line is the CDF. You can see that blue line. So the line is more step, means there are much values in this range, but if this is flat, means these values are sparse. That means less number of values, right? So and PDF is probability density function. So the weights are like in this bell shape architecture, like bimodal in this graph. So in this region the values are more. So if we use density and random initialization, what they will do, they will select the representation like cluster centers from the high density region, you can see, but then the outliers will be removed. So then for this value, what we need, what will happen, the accuracy will be lost. So that is why they use a linear initialization, minimum value and maximum value. In this way, we have the representation from all numbers, as well as the high density value and the low density value. Okay, go next. So in this work, they also do some analysis why Huffman coding works. So if we check these weights, for example, these are the weights, okay, after pruning and quantization. So 0 to or 1 to 31 or 0 to 31, we can see that some weight index have more uses and some weight index have has less uses. So for example, this 9, 7, 8, these weights has more than 75,000 times. So that is why if we want to store one by one, we may need we need to use redundant space. But if we use this Huffman coding, like lossless compression, then we can only store their number or weights only one time and reuse them again and again. Okay. Okay.
Okay, so now let's discuss the data sets that was used in this paper. So how many of you are familiar with the MNIST data set? Yeah, most probably everyone. And how many of you are familiar with the ImageNet dataset? Half of them?
Yeah. This
Okay, so next. So this is what the dataset looks like. So for those of you who do not know the MNIST dataset, this is the hello world of computer vision. So it contains grayscale images of handwritten digits from 0 to 9. And then this MNIST dataset was used on the smaller models, Lineage 300, which is a fully connected network, and Lineage 5, which is a classical CNN. And the ImageNet dataset is a large complex dataset, and it contains like 1.2 million pictures across 1,000 categories. So the MNIST dataset just has like 10 categories, but the ImageNet dataset has like 1,000 categories, like spanning from dogs, cats, cars, mushrooms. If you can see in this part of the picture, you can see like all kinds of stuff. There is like carpet, there is flowers, there are eggs. So this is the more complex data set. So they used one simple data set and one complex data set. And this complex data set was used for AlexNet and VGG16. So I just wanted to give a overview of the code basis of the models. So before we read the paper, we went and checked to the models. So we found all these models on GitHub. So this is for Lineage 300 and Lineage 5, along with the GitHub links. And we also checked the AlexNet and VGG implementation to better understand the model before we dived into this paper. And next. Okay, so so this is the important part. So the framework that they used in this paper is the CAFE framework. And you can easily find this framework on GitHub, download it and use it. And that is the logo of the CAFE. So this is just a deep learning library like PyTorch or TensorFlow. And no, on the back. So yeah, at that time, this paper was published. This was considered one of the best libraries for computer vision tasks. And this is also optimized for performance, especially when GPUs are utilized, which is in this case, as is capable of processing large data sets. Previous one. Okay, so now let's discuss the benchmarking of this for speed up and energy. So the main important thing was the performance was not simulated. So all of these experiments were run on real hardware, and the hardware that it was run on is Intel i7 CPU. Probably everyone has heard of this, but the NVIDIA Titan X GPU and Tegra K1 mobile GPU might sound new. And the libraries that they used was vendor optimized libraries, Intel MKL and NVIDIA sparse. So Intel and NVIDIA like make special libraries for special research purposes, like focus on individual research based on the collaboration. So these libraries were specifically built for this research only. And I just want to go through the implementation steps. I mean, this was already explained by Rahat and Apu, but I just want to like go through it again. So pruning was implemented by using a binary marks on network blobs, which block the gradients and then update the pruned connection. And quantization was implemented by using a weight sharing code book and a group by index step, which can be used to aggregate the centroid gradients before updating. And Huffman coding is applied after the retraining, and no additional training is required for this phase. So now let's discuss the metrics that were used in this paper. So there are two metrics, mean top 1 error and top 5 error. So the top 1 error is the more strict test, and the top 5 error is the forgiving test. So what top 1 error means is like the model, it will only have one guess. Like if you guess, if the suppose the image is leopard, but the top guess is cheetah, which is wrong. So if the top guess is wrong, then it's considered a top 1 error. And the top 5 error is more forgiving. It's like you get 5 guesses. And if if your guess is any of the top 5, then it's considered a success. If not, then it is considered a top 5 error. And next. So the way they have used these metrics in this paper was, for MNIST only top 1 error is used, because if you really think about it, there is just 10 categories in the MNIST data set, and a top 5 error means like a model didn't predict it properly in its first 5 guesses. So you can guess like the accuracy is straight up less than 50%, or let's say 50%. So this is not a good metric to measure for the MNIST data set. But for the ImageNet, it works perfectly well, as ImageNet has like 1,000 categories. So in this, the top 5 metric is very important for the image, for this part of the paper. Okay, so now let's discuss the results. So this is a table from the paper, and as you can see, so all 4 of the models are present here along with their compress rate. So I'll be explaining each one of them in the upcoming slides. So the major result here is that they were able to achieve massive compression with no loss of accuracy. And all of the models compressed can be easily stored on the on-chip SRAM of a mobile phone. So let's start with the simplest model, Linear 300, which is a fully connected network. And so first, when pruning was applied, they were able to achieve a 12x reduction, reducing the parameters from 266,000 to 21,000, which is very good. So from this example, you can guess like how redundant a particular network is. I mean, the parameter reduction here is just insane. So for the then quantization was applied, and all the fully connected layers were quantized from 32 bits to 6 bits. And after this, they were able to achieve a total of 32x compression. And after applying Huffman coding, the final compression was 40x. So the main result of 300 on MNIST was it was reduced 40 times with improved accuracy. Actually, if you really look about it, just the reference is the original model and the compress is the new compressed model. So there is slight improvement in the accuracy. And now the Linear 5. So this is the one with a convolution network in it. So pruning so first up, after applying the pruning, they were able to reduce the parameter from 431,000 to 34.5 thousand, resulting in 12x reduction. And in the quantization part, now this is a bit different. So as we can see from here, convolution layers were quantized to 8 bits as opposed to the 5 bits. This is because convolution layers are sensitive and they carry important information as opposed to the fully connected layers, which has more redundant information. The same back one. So and the fully connected layer were quantized to 5 bits. And after this, the total compression was achieved to 33x. And after applying Huffman coding, the final compression went to 39x. And so in the end, they were able to reduce this model 39 times from 431,000 parameters. I mean, the size here, if you see, the original size was 1720 kb, but the final result here after 39x reduction is 44 kb. And the accuracy, there is slight improvement in the accuracy. There is improvement in accuracy because all of this is running on SRAM as opposed to the DRAM. So because of that, we can find a little bit of improvement in accuracy. So now the big leaks, the AlexNet one. So this is the big model, and this contains 61 million parameters. And this is one of the popular deep learning models. So first, from pruning, we were able to achieve 9x reduction here. And if you see here, the parameters were reduced from 61 million to 6.7 million. So so even for a like a model with million parameters, this is the case, then we can only imagine like how much redundant parameters there are in like GPT models, which are like 70 billion parameters or like 40 billion parameters. So and the quantization process is the same as earlier. So the convolution layers were quantized to 8 bits and the fully connected layers were quantized to 5 bits, similar as the previous example. And after this, the total compression was achieved 27x. And after the Huffman coding, they were able to achieve a total of 35x reduction with no accuracy loss. So the size was reduced from 240 MB, now 6.9 MB. So this is very important in the case of this paper, because this 240 MB could not be stored in an on-chip SRAM, because an on-chip SRAM only consists of very few megabytes of storage. But now the 6.9 MB can easily be stored on an on-chip SRAM. So this was one of the good result that they achieved here. And again, no loss of accuracy. Okay, now this is the final model that they use, and this is like the crown jewel achievement of this paper. So as you can see, this model has 138 million parameters. And there is a lot of bloated, fully connected layers in this model. So that's why the pruning here was, the pruning achieved the highest reduction here, because 13x reduction, more than all the previous examples. And it was reduced from 138 million to 10.3 million. This was because this particular model consists of bloated, fully connected layers. And the quantization steps are similar to previous one. The same thing is happening here, quantized to 8 bits, quantized to 5 bits, and the total compression achieved was 31x. And after Huffman coding, they were able to achieve a total of 49x compression. So the original model was 552 MB, but now they were able to reduce the size to 11.3 MB. And for the error, there was actually slight improvement in the error, if you see here. So this is the total result of this paper. Now Rahat will continue the rest.
Okay, so far we discussed the result. So we want to analyze or discuss a little bit this result and based on some evaluation study. So first is that impact of the compression on accuracy. So here we see that if use the singular value decomposition, then you see that if you compress more than 40%, then you may lose the accuracy around 4.5%. So and this is the worst we can say among the four compression technique: pruning, quantization together, and only pruning, only quantization, and SBD. So, but if you apply the pruning and quantization together, then we have the better result. Even you compress more than 3%, you can have a you can retain the around same accuracy, a little bit change. Next, we discuss the bit reduction on accuracy. What the impact of bit reduction? Bit reduction means quantization. If you apply the quantization, that means you are using the fewer bits for the weights. So here is the one thing: if you apply the this reduction across the fully connected layer, you can reduce around to 2 bits until you have a sharp drop to the accuracy. And but for the case of the convolution layer, you see that there is a it's around, at least you need 3 bits per weights for the for maintaining the accuracy. So and if you use the overall all layers, if you want to use the same quantization, then you have to actually use around 4 bits per weights for the maintaining the accuracy. Otherwise accuracy will drop. This is the observation. So here is the pruning works well with quantization. So because pruning, if you do pruning, you are reducing the number of the weights, and quantization means you are reducing the number of bits. So if you apply, we have a question later. So combination layer require more bits of precision than fully connected layer. What might be the reason? So any guess that what's the reason that we need more bits for the combination layer?
Quantization work on the prune network instead of the whole network. What is the reason?
Not like this, but if you apply the two type of layer, fully connected layer, convolution layer. If you apply the same quantization to the convolution layer and the fully connected layer, then the reason behind it that in neural networks, convolution layer actually hold the more important and more special features. So if you reduce the number of bits for this layer, that means it is may lose more important information. So because you are do some quantization, that means you are actually losing some information. That's all time true. But if you do this same things for the fully connected layer and convolution layer, and then convolution layer will affect the more on accuracy. Okay. Centroid initialization, this is another thing, because if you want to the quantization, then you have to do the share the weights, and then you have to do the clustering the weights. So there is a different way to start the clustering. This is the different way. This is the uniform initialization or random initialization, or the what is this density initialization. But random, if you do the random initialization, what might happens, we see that all times if you do the uniform initialization, you have a better accuracy compared to other two. The reason behind it is, if you do the linear initialization, in these cases the centroid initialization will be distributed from the minimum value to large value. So because large centroid means that large weight means that is more important weights. That is the common idea. So but more important information may be less than some less important information. So so if you do the other random initialization, that means there may be like this, that some nearest largest weights can be assigned to the nearest lower or smaller weights. So in this case, you are actually maybe losing some input information. But if you have a linear initialization, that means you are making the some centroid for the large weights and large centroid. So this means you are actually holding some input informations. This is the main regions. Some effect of compression on speed up. So if you do this, that papers mention that they achieve the 3 times speed up on CPU and 3.5 times on GPUs and 4.2 times on mobile device. And energy efficiency means you have a less energy to do the operational computations, as you are now can feed the models in the SRAM. That means it is very nearest to the CPUs, and then you have some gain in the energy efficiency. They mention here they around get the 7 times less energy on CPU and 3.3 times less on GPU and 2.4 times on mobile device. And there is the overall comparison with the others previous methods. With these methods, we see that prunings and quantization and Huffman, if you apply these three compression techniques together, they show that they have a better compression rate without losing any accuracy. There is 35 times reduction. Okay, we talk about some strength and limitation of the papers. So strength, I can say that main strength is that massive compression with zero accuracy loss. So you are reduction the whole models around 35%. You have a zero loss. This is the I think biggest matters in this compression on other compression techniques. And as you had compressed them, as a you need lower less space, then you can fit them on the SRAM. So this is the another things. So we want to say that some improvement of this limitation is that one is that unstructured sparsity. So these papers main another main limitations is that unstructured sparsity. That means you do the pruning, but actually you are making the less important weights to the zero. So you are not actually removing the connection. So our whole networks is here, but you are removing the you are changing the less importance to 0 0 0 0. That means we are technically we are thinking that this is the prune, but not is the prune. So this is called this pruning creates a sparse network. That means your sparse computation. There's some problems on the hardware. So some hardware does not support this type of sparse matrix or like this. So there is some improvements in later. There's some papers they use the some structured pruning. That means they also do some minimize the model size, actually reducing the model structure, and also some papers do some they change the sparse matrix into in a structured way so that they can fit the hardware. So another thing is that limitation is that I think there is the limited to weights only. So this is only used for the compression for weights, but in current some methods they apply the compression to also the activation layer. Last, we want to talk that these papers actually only concern on the CNN. So CNN structure, they don't have any study on the LLM. Some papers do some try to apply some quantization and pruning quantization to LLM models. Okay, key takeaways. If you say that compression is a multi-stage process. So if you do the compressions, so you cannot find the one techniques that work that can beat all things. So, but if you combine them, each technique has its own benefits. So if you combine them, you might get the better benefits. Another thing, massive size reduction without accuracy loss. So current techniques and previous some methods, they actually reduce the model size, but accuracy still hold. This is the great things. And hardware efficiency gain. So if we, in our before the 10 years, actually our memory size is much lesser than these times. So these times, this is a very good concern that how big wanted to store in the memory. Even nowadays, if you think that GPT 4.5, this is a very big memory, you cannot think about it. So this is the things. Another takeaway is that is a structured sparsity limit hardware speed up. So in this case, there's a good thing is that we have some new papers that do the some structured pruning that improve the sparsity. So another drawbacks, we can say that prunes, retrain, quantize, retrain is a slow and expensive. So you are doing same things again and again. So some methods show that solution like this, that they actually do show the some one step joint pruning and quantization that's improve the this efficiency, that they improve the iterative efficiency. So that means less number of iteration. Okay, thank you. Thank you.
Okay, actually main presentation is done. So now who said I don't know, but someone said like from reviewer, I don't know, like I don't trust your paper. If you have source code, give me. Okay, that is why I checked their paper. Actually it works or not. So these are the this is the GitHub repo, and I run their code, and we need to use this command and prepare the environment. And by running their project, we go next. So what I found that I ran the like LANet 300/100 network on the MNST like data sets, and actually we found that for a fully connected layer, weight was like 2,35,000, but after pruning it actually 10,528. So this is I got. Go next. So that means yeah, go next. Yeah, so go next. So then also is another program is weight sharing. So I also ran their code and found that. So if we like have more accuracy, then more storage we need. Like we need correct. Yeah, the weight value is like higher, but if we like a slightly lower accuracy, then we may need to save storage. I go next. So this is the like Huffman coding result. We can see that before the total bytes needed 97,000, and now after using the Huffman coding, we only need 26,000. Okay, go next. Okay, any questions? No questions? Yes.
I'm not exactly sure about that.
Yeah.
In the paper, they mentioned that this is because of now all the operations are moving.
I think the reason may be like this, that actually general perception is that if you do compression, you manual some. That means we are general expectation that the accuracy may be a little bit compromised. But I think it may be the reason of the, if you do some pruning, then model may be overfitted, it may be get good general. So as
You
you are
showed
pruning,
that
so it may
accuracy
be more
increase on your part.
that's reason maybe
Accuracy increase.
so even you know that that's maybe
Zero.
not
Not much.
not the case. But
Zero
then
accuracy.
given this, give it some pruning that means you have a overfitted.
Yeah, your question actually good. Yeah. So we saw that this is a like mixed behavior. So always it doesn't increase. So sometimes it increase, and sometimes I show in the like code run the accuracy slightly decreased. So we compress the data, but it will not always increase the result like accuracy.
This is
Yeah.
manual.
Not randomness. This pruning and quantization actually based on the back propagation. I showed you. So they first prune the network, then retain the network like by doing back propagation to reach until the accuracy they got, or some like threshold, using some threshold, maybe some percentage they stop. If they like run 20 for no improvement, then they will stop. Okay. So any other questions? No questions?
So this times maybe not very important, but from
Okay, go
after 10 years back,
Econax? Or I should ask.
I think that difficult to answer, but if the paper is 10 years back, but we can show that this has a good impact in the next paper, because I see some papers currently proposed that do some modification strategies, such as limitation of the experts metric. So they need to convert the experts metrics to the more efficient one. That
Yeah.
so there's some questions Thomas, that is that why is the energy often dominated the on-chip RAM SRAM access rather than off-chip DRAM access? Right. But SRAM is more close to the
It is also described in the previous paper.
I think this is the
Yeah, that's right.
The thing is that if you though this is near to the queue, but it's frequently used when compared to the distance distance memory that given.
So
overall,
yeah, I also in the previous like presentation like question, I also answered the same question. So sometimes we think that like accessing DRAM actually too costly, but even if we like access too much data like stored in the on chip SRAM, then it will also create overhead to the memory and the energy. Next.
Huffman coding effective for model.
Okay, this one is actually
I think
from the lecture. So anyone?
Huffman coding effective for model. Okay, this is the. I think this is the correct answer. Or you have a most frequent most frequent numbers get the lowest lower number of bits. That is the answer.
No. Can you repeat?
Most frequent ones.
Actually, not like that. So you are too close. But the main idea is like why Huffman coding like effective for model compression. So after like quantizing the weights, there will be too much repetitive numbers, right? So we like the weights like for a single value, for example, weight is 32. Like this is index, so that will be like 1 lakh times. So if we like store the 1 lakh times like the same weight, then the memory will be like take like more memory. But if we use the like lossless compression Huffman coding, then it will like utilize this issue. So this is the same thing.
Different
Yeah.
I think you should give some.
Okay, go next.
Last question is why speed up and energy efficiency does not scale with compression rate that much? That suppose you compress it around 49% compression, but energy speed up is around 4 times or 5 times.
A bit. Okay, if there is anyone want chocolates, we can we can share this. Okay. Okay. Two.
Reducing actually all the paper, their main focus on the I think that how to reduce the time. And by this process, because you can reduce the space time, as this actually create a sparse network without changing the structure, you are have a all the core network that do it, and you have to do the same from maybe if you have a human system that might have a movie, but you need to do.
I think
That's a reason I think that
it will take a little bit longer, but it is okay.
I think it is okay, bro. Yeah, even not much longer.
Okay. That's the thing. You want to say that how you use the efficiency. 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 You
Bias, I think if bias is like different, they discuss about.
I think that's okay. Bias.
They did not like discuss about the like multiple bias. If it is single bias, then I think it is not problem.
I think mainly it comes from the zero market. If you do something, you multiply something, that is the maybe special computation technique. What that's like. If you have the multiplication of the 0.0001225 multiply 0.0000125 and then 0 multiply 0.01, that's the so some energy efficiency and speed of transfer, I guess, but it's really negative. Yes, that's already.
The bigger question. Whenever we talk about compression,
Actually,
Decompression.
decompression means may not be related. We do some compression in the neural networks or the you can say the diffusion model that we compress the big image into the latent space, then using some models, and then we can back to the original size. Suppose 51 by 50 12 by 12 by 512 image to compress to the 64 by 64 size. And then we do the some our processing, and then we get the output. We do again the rescale, and then back to the original size. This is called auto-encoder concept. This is what I know in the deep learning theory, but in traditional compression technique, file compression, there's some other technique. This is the Huffman.
It depends on if you say if your cosine change a little bit. For example, how can we like use the lossless decompression? So I showed the Huffman coding. So Huffman, by using the tree, if we read the numbers, like locate the number by using paths, then we will get the exact same value. So this is called actually decompression. So and the lossy compression explained, yeah. We can predict something, yeah.
so
I think this is lossless compression, and if we get back after fine tuning the original accuracy, that's I think that's not
No. This paper actually like trained on two things, pruning and quantization. But in the Huffman coding, there is no training. So that is why they use the lossless compression instead of lossy compression. Because in the first two things, pruning and quantization, they can prune and retain the model to keep up the accuracy.
So it cannot be go back to the original.
did they discuss any other method?
No. They talk
Quantization.
after quantization, they add actually Huffman.
Huffman.
Huffman coding is the addition the previous paper that the pruning quantization that Huffman coding.
You can check and pass. Anyone?
We got to vote. You have 1 minute. Please send the email right away.
So we need to send also email, right? Yes, sir.
Give me a second. I'll take